In this video, we will talk about categorical data in Pandas. First off, what is categorical data? So here we can see a normal Pandas series in which we have some strings A, B, and so on. And we can represent this data as categorical data because we can say that each of the elements belongs to a certain category. So we have the category A, B, and C. And in order to make Pandas understand that we have these categories, we pass the D-type category. So if we run that, then we get a normal series, but the D-type, so the data type of that series, is category. So each of the elements belong to a certain category, and we have the categories listed here, so A, B, and C. Now, why do we care about these categories? One of the main benefits is that we have a lower memory usage. And before we go on showing how much lower the usage is, we can also think about how it makes sense intuitively. So without categories, if we have a series that, let's say, is 100 elements long, then we would have to store 100 elements individually. And so even if some of the elements are the same, so they're not adding new information, they will still cost additional memory to be stored. So there will be a huge difference if we store 1A or 100 A's. And now going to the categorical data, if we have categories, then we can just say we want 100 elements from this or that category, and the actual category we just have to store once. So that's the rough idea behind why the memory usage is lower. Now you're probably thinking, how much memory are we actually saving? And so in here we are creating a data frame with two columns, floats and food. The float column will have 100,000 floats, and the food column will have 100,000 food items of either pizza, burger, sushi, or tacos. And we can run that and then use the memory usage to check how much memory each of the columns are consuming. And we see that the float column only takes 0.8 megabytes, while the same amount of string items takes 6 megabytes. So around 10 times more. So now let's make this food column categorical. And we do that by calling on the data frame as type, and then we define in the dictionary which column we want to change. So that's our key here, the food column, and then the value determines the new type of that column, which should be category. And then we check the memory again. And this time the food column only consumes 0.1 megabytes. So we reduce the memory usage by 60 times. And it doesn't just stop here, because the performance also gets better. So here we want to turn all the food items into uppercase letters. And this here is our old data frame without the categorical series. And if we run this here, it takes us 10 milliseconds. And now we run the same function on the data frame with the categorical food series. And here it takes about 600 microseconds, which is then about 20 times faster. However, there is a problem. If we check the memory usage again on this new series, where all the food items got turned into uppercase, then we can see we went back up to the 6 megabytes. And that is because our food series is not of type categorical anymore. So here we're checking the D type after the function was applied on the categorical series, and it returns us object. So even though at one point the memory usage was lower and also performance increased, the peak memory usage is still at the same value. So it could still crash your system if we're dealing with a lot of data. So what is the solution to that? The solution relates to the idea how categories are more memory efficient, because we said we don't store all the elements individually, but rather just the information from which category they are. And so when we want to apply some function, we also don't want to operate on the whole series, but rather on the respective categories. So what we're going to do here is we select the food column, we get the categories, and we rename them with the string.upper function, which then turns all of the food elements into uppercase. And if we now time that, we're down to 50 microseconds, which is 10 times faster than our previous approach. And previous referring not to the first approach, but to the already second faster one, so this one here. And also our data is still categorical. So we check the D type here and it tells us category. Besides the things we saw here, there are some more tricky things that can come up when merging data frames or while doing other things. And if you're interested, you can check that out here. In the food data, we didn't have any ordering. So of course we could have said one item might be larger than another one, but that's just one perspective, and we could also talk about price, calories, or other things. But since we just talked about the foods themselves, there was no order. if we now have data that implies some order, such as the words low, medium, and high, then it would be great if we could order our categories. And to do that, we first create our series as we would normally, and then we also create our categories and pass both of that to pd.categorical. And now if we want that order to apply to our categories, then we pass true to the ordered argument. And if we run that, then we can see here our series as it was initialized here. And also we have the dtype category, but now it's not just listing the categories here, but we have these comparison signs here that tell us that low is less than medium and medium is less than high. And so this is also the order that was specified here. In this cell here, we're initializing another series, and we're doing that to show off some of the functionality that comes with this ordered data. So because our data is ordered, we can apply comparisons such as smaller, bigger, smaller, equal, and also min, max, and sort values. So we run that, which gives us a Boolean series, min, max, gives us the minimal and maximum value, and sort values will sort the values in our series. Very often the data that we're starting out with will not be categorical, and sometimes it can make sense to turn numeric features into categorical ones. One example here is from the Titanic dataset, and here we have the age column, and while the specific age might be important in some cases, it might also very well be true that we're just interested if the person is young, middle-aged, or very old, or maybe if they're underage or not. And we call this process of converting numeric data into categorical data binning, because essentially we're creating bins, so categories, that we put our data points in. Okay, let's have a look at the age column and also the first 5 values. And now we want to cut the ages into bins. So we call the pd.cut, pass the age column, specify how many bins we want, in this case 3, and then we'll look at the first 5 values. So we'll see here now a lot more numbers, but don't be confused, so we need 2 values always to specify one bin, so the left boundary and the right boundary. And we can also see these bins and their boundaries in here. So the first bin goes from 0.34 to 26.9, then from the 26.9 we go until 53 and then so on. And so then each of these values falls into one of these bins. And by default, the size of these ranges will all be equal. So there's the same distance between this boundary and this boundary as it is between this and this boundary. So all our bins are equally sized. If we don't want that to happen, because maybe we want to specify if a person is underaged, then we pass to the bins argument not just a single value, but our custom boundaries. So now we want one bin from 0 to 18, another one from 18 to 67, and then a final one from 67 to 80. And now if you run that, then you have the categories almost 0 until 18, 18 to 67, and then 67 to 80. One thing to look out for when we set the edges manually is that we cover all of our data points. So in here we're just going from 64 to 80, and that will mean a lot of the data points cannot go into any bin, so they will be nans. Another cool thing is that we can pass labels. So in here our categories have these weird representations, but we can also give them proper names. So it doesn't make a lot of sense for these bins here, but in theory we could have the label child, grown up, and then senior. So let's put that all together. Here we cut our age column into these specified bins, and let's change 17 to 80 to make sure they're actually children. And then we pass also the labels child, grown up, and senior, and we assign that to a new column. So let's run it, and we still have a nan in here, but that's not because of our binning, but because the value didn't even exist before. We said that the default cut will make bins that are of equal size. There's another function called qcut, and this function will also create bins depending on how many we define, but it will cut these bins in such a way that we will have an equal amount of elements in all of the bins. So this now tells us that there's an equal amount of people aged between 0.4 and 20 years, and 20 years and 28, and so on. If you're looking for some more info, you can check out this blog post, which was also referenced before. And as said before, this will show you some more common pitfalls, and it also includes some cat pictures.